On November 3rd, 2025, something from another star system swept past Venus so closely that scientists around the world stopped what they were doing and watched. What happened during those hours defies every prediction astronomers made about this encounter, and some of what was observed still doesn't have an adequate explanation. You're probably thinking Venus gets visited by space objects all the time. Asteroids, comets, solar wind, cosmic dust. Our neighbouring planet has seen it all. But this wasn't just another flyby. This was an object that originated from beyond our solar system, carrying material forged in the furnace of an alien star, travelling through the cosmic void for potentially millions of years before arriving at our doorstep. And when it passed Venus, multiple spacecraft positioned throughout the inner solar system captured data that has sparked one of the most fascinating scientific debates of the decade. Here's what makes this moment unprecedented. We've only confirmed 3 interstellar visitors in all of human history. 3. The first was Oumuamua in 2017, which baffled scientists with its bizarre acceleration and elongated shape. The second was 2I Borisov in 2019, which behaved more like what we expected a comet to act like. And now we have 3I Atlas, the third confirmed messenger from the stars, and it just performed a close encounter with one of the most mysterious planets in our solar system. But that's not what's keeping astronomers up at night. What's generating heated discussions in scientific circles is what happened after the flyby. Images captured in late November revealed features extending from 3I Atlas that shouldn't exist according to conventional comet physics. Straight lines projecting sideways over vast distances. Temperature readings that don't match what happens when icy bodies approach the sun. Trajectory characteristics that have divided the scientific community into camps, with fundamentally different interpretations of what we're witnessing. Stay with me, because in the next minutes we're going to examine verified astronomical data, explore the scientific controversy surrounding this visitor, uncover what spacecraft observed during the Venus encounter, and investigate why some researchers believe 3I Atlas represents something far stranger than a typical comet. We'll separate confirmed facts from speculation, present multiple scientific perspectives, and explore what this close encounter with Venus might reveal about visitors from other star systems. Let me ask you something. When was the last time you heard about an astronomical event that made NASA, the European Space Agency, and astronomers from multiple countries simultaneously redirect their attention and resources? When was the last time a Harvard astrophysicist publicly questioned whether something travelling through our solar system might not be entirely natural? That's the level of scientific mobilization and controversy we're talking about here. The Venus encounter wasn't random. The trajectory 3I Atlas followed brought it through the inner solar system along a path that aligned remarkably well with the orbital planes of our planets, a detail that some scientists find statistically curious. And the timing. Multiple spacecraft happened to be positioned in locations that could potentially observe different aspects of the flyby. Europa Clipper was making its way toward Jupiter. Hera was in the vicinity after its asteroid mission. SOHO, Parker Solar Probe and Solar Orbiter all had viewing opportunities from their positions monitoring the Sun. Even Hubble was scheduled to perform ultraviolet spectroscopy observations. This level of coordinated observation capability is rare. When an interstellar visitor approaches, you can't just send a mission to intercept it. These objects move too fast, appear too suddenly, and follow trajectories we can't easily match with our current propulsion technology. So we observe them with whatever assets we have available, gathering as much data as possible during their brief passage through our cosmic neighbourhood. And for 3I Atlas's Venus encounter, we had more eyes watching than we've had for any previous interstellar object. What those instruments captured has generated questions that remain unanswered weeks later. Some observations match what scientists expected, others don't fit neatly into existing models of how comets behave when heated by solar radiation, and a few features have sparked genuine scientific debate about whether our understanding of interstellar objects needs fundamental revision, or whether we're witnessing something that challenges our assumptions about what travels between the stars. Here's what I want you to understand before we go deeper. This isn't a story about aliens or conspiracy theories. This is about legitimate scientific mystery, about astronomers looking at data that doesn't quite make sense within conventional frameworks, about the tension between sticking with established explanations and remaining open to observations that suggest something unusual is happening, about how science actually works when confronted with phenomena that don't fit perfectly into existing boxes. The scientific method demands we follow the evidence wherever it leads, even when it leads to uncomfortable questions. And right now, the evidence from 3I Atlas's encounter with Venus is leading different qualified scientists to very different conclusions. Some see a perfectly normal comet exhibiting known behaviours that appear strange only because we're seeing them for the first time in an interstellar context. Others see anomalies that require explanations beyond standard comet physics. And a few are asking whether we can definitively rule out possibilities that might seem extraordinary, but deserve investigation based on the observed data. If you're fascinated by the mysteries of space, by scientific debates unfolding in real time, by the possibility that our solar system receives visitors we're only beginning to understand, then hit the like button right now. Drop a comment telling me what you think happened during that Venus flyby. Do you trust the conventional explanations, or do you think something stranger is going on? Your engagement helps this investigation reach others who want answers to the same questions we're exploring. Because this isn't just about one object passing one planet. This is about humanity's growing awareness that we live in a galaxy filled with travelers from distant stellar systems, and we're just learning how to recognize and study them. The story of what 3I Atlas did to Venus begins with understanding what made this visitor so special in the first place, why its trajectory brought it to our neighbouring planet at this specific moment in time, and what scientists were hoping to learn from this once-in-a-generation observation opportunity. So let's start by examining the visitor itself, where it came from, what makes it different from solar system objects, and why its arrival generated so much scientific attention even before the Venus encounter happened. Before we dive into what happened at Venus, you need to understand what makes 3I Atlas fundamentally different from anything you've seen streaking across the night sky. Every meteor shower, every comet you've heard about, every asteroid that makes the news because it's passing near Earth, all of those are members of our solar system family. They were born here, formed from the same primordial disk of gas and dust that created the Sun and planets. They've been orbiting within our cosmic neighbourhood for over 4 billion years. 3I Atlas didn't form here. It's a refugee from another star system entirely. Think about what that means. This object was shaped by conditions around a star we can't even identify with certainty. It contains materials and compounds that were forged under different stellar radiation, different temperatures, different chemical environments than anything native to our solar system. For potentially millions of years, it drifted through the vast emptiness between stars, travelling through a void so enormous that light itself takes years to cross the distances involved. And then, in a galaxy containing hundreds of billions of stars, its trajectory happened to intersect with our solar system. Not a collision, but a gravitational interaction, a cosmic encounter that bent its path through the Sun's influence before sending it back out into the interstellar medium. These visits are theoretically common. Scientists estimate that at any given time, several interstellar objects might be passing through the outer reaches of our solar system. Too distant and too faint for our telescopes to detect. But confirmed detections, those are extraordinarily rare. That's because spotting an interstellar visitor requires incredible timing and luck. These objects move fast, faster than anything gravitationally bound to the Sun. They appear suddenly, spend just months crossing the inner solar system, where our best telescopes can observe them, and then vanish back into the cosmic dark. You need automated sky surveys constantly scanning the heavens, sophisticated algorithms identifying objects with unusual trajectories, and rapid follow-up observations confirming the interstellar origin before the visitor gets too far away to study effectively. Only 3 times in human history have we successfully identified and confirmed an object following a hyperbolic trajectory that clearly originated from beyond our solar system. Oumuamua arrived first, tumbling through our space neighbourhood in 2017 with an elongated shape and mysterious acceleration that still generates scientific papers. Then came Tui Borisov in 2019, a more comet-like visitor that behaved much closer to astronomers' expectations, and now 3I Atlas, the third confirmed interstellar messenger, carrying with it mysteries that rival even Oumuamua's strangeness. What caught everyone's attention wasn't just that 3I Atlas came from another star system. It was the trajectory this visitor followed as it approached the inner solar system. Interstellar objects can enter from any angle, any direction. The galaxy doesn't impose preferential paths. Yet 3I Atlas's trajectory aligned remarkably well with the orbital plane of our solar system's planets. Not perfectly, but close enough that some astronomers noted the alignment in their observations. Is that significant? Here's where scientific interpretation divides. Most astronomers would tell you that, with enough interstellar visitors, some will inevitably follow trajectories that appear aligned with our planetary system purely by chance. It's a statistical expectation, not evidence of anything unusual. But a minority of scientists find the alignment curious enough to mention, especially when combined with other observations that have emerged since the Venus flyby. The real attention came from the scientific opportunity this trajectory presented. Because 3i Atlas's path brought it through the inner solar system where multiple spacecraft and telescopes could observe it under optimal conditions. This wasn't a distant flyby through the outer solar system where only our most powerful instruments could catch fleeting glimpses. This was a close approach that would bring the interstellar visitor near Venus, near enough that scientists could potentially detect interactions between the comet and the planet's thick atmosphere. NASA took notice. The European Space Agency prepared observation campaigns. Ground-based observatories scheduled tracking time. This was a chance to study interstellar material up close, to analyze the composition of matter from another stellar system, to compare an interstellar comet with the comets we know from our own Oort cloud and Kuiper belt. Every measurement, every spectrum, every image captured during this flyby would contribute to our understanding of what else is out there in the galaxy beyond our sun's influence. But here's what made the scientific community truly mobilize. The Venus encounter window coincided with favorable positions for multiple spacecraft that could contribute data from different vantage points. Europa Clipper was making its journey toward Jupiter, positioned where it might even pass through 3 Atlas's extended ion tail. Here a spacecraft had viewing opportunities. Solar observatories like SOHO, Parker Solar Probe and Solar Orbiter could track the visitor's behavior as it approached perihelion, the closest point to the Sun. Even Hubble was brought into the campaign. Ultraviolet spectroscopy observations were planned to analyze the comet's gas emissions, to understand what volatiles were sublimating off its surface as solar radiation heated the ancient ice. Every space agency with assets in position wanted to capture some piece of this rare opportunity. Think about what that level of coordination indicates. These aren't enthusiastic amateurs getting excited about a space rock. These are professional astronomers and planetary scientists recognizing that interstellar visitors come so rarely that every observation counts. We might not see another confirmed interstellar object pass this close to a major planet for decades. This was a moment to learn everything possible while the opportunity existed, and then November 3rd happened. The flyby window arrived. Instruments collected data. Scientists waited for downlinks and signal processing, and what emerged from that data has been sparking debate ever since. Before we examine those observations, you need to understand what Venus itself is like, because the planet 3i Atlas encountered is one of the strangest, most hostile environments in our solar system. Venus isn't just hot or cloudy. It's a world that represents an extreme version of what planetary atmospheres can become. And when an interstellar visitor passes close to a planet like that, the question isn't whether something interesting happened. The question is whether we had the right instruments in the right positions to detect it. Venus has always been Earth's evil twin. Same size, same mass, same basic composition. But everything that went right for Earth went catastrophically wrong for Venus. Where Earth has moderate temperatures and liquid water oceans, Venus has surface temperatures hot enough to melt lead. Where Earth has a breathable atmosphere, Venus has crushing atmospheric pressure and clouds made of sulfuric acid. It's what happens when a planetary greenhouse effect runs completely out of control. But here's what most people don't realize about Venus. Despite being a hellish environment at the surface, the planet's upper atmosphere is one of the most dynamic, complex atmospheric systems we've ever studied. Massive cloud patterns circle the entire planet in just a few days, driven by winds that dwarf anything on Earth. Atmospheric waves ripple through the dense carbon dioxide envelope. Temperature variations create circulation patterns that scientists are still working to fully understand. Japanese satellites and various meteorological monitoring systems have been tracking Venus's atmospheric behavior for years. Before November 2025, those observations showed the patterns scientists expected: normal planetary scale waves, consistent temperature distributions in the upper atmosphere, the sulfuric acid cloud layers maintaining their characteristic structure. Venus was behaving like Venus always behaves, mysterious in its details but consistent in its overall patterns. Why does this matter for our story? Because when something external influences a planetary atmosphere, the effects show up as deviations from baseline behavior. And Venus's atmosphere, despite being thick and massive, is actually quite sensitive to external influences. Solar wind changes, magnetic field interactions, even the passage of cometary material, all of these can potentially create measurable effects if they're strong enough and if we're watching closely enough. Scientists understand this. That's why the Venus flyby generated so much interest. An interstellar comet passing close to a planet creates a natural experiment. Will there be measurable atmospheric effects? Will the comet's extended ion tail interact with Venus's atmospheric envelope? Will spacecraft positioned correctly detect changes in atmospheric composition or temperature patterns? Venus doesn't have a protective magnetic field like Earth does. That makes its upper atmosphere more vulnerable to direct interaction with charged particles and plasma structures. When a comet approaches, it carries with it an extended tail of ionized gas, plasma that stretches for enormous distances behind the comet's nucleus as solar wind pushes the sublimating material away from the Sun. If that plasma tail happens to sweep across a planet, the interaction can create detectable effects. Earth has experienced this. Historical records document times when Earth passed through the debris streams of comets, creating spectacular meteor showers and even measurable changes in our upper atmosphere's chemistry. Venus, lacking Earth's magnetic shield, would theoretically be even more susceptible to such interactions if they occurred at sufficient intensity. The question scientists were asking before November wasn't whether interaction was possible. It was whether 3I Atlas's flyby trajectory and distance would bring its plasma tail close enough to Venus to create measurable effects. Predictions varied. Some models suggested the geometry was favourable for at least some interaction. Others calculated that the distances involved would make any effects too subtle to detect with current instruments. But everyone agreed on one thing. This was worth watching. Because even if no dramatic effects occurred, the observations would still yield valuable data about how interstellar comets behave in the inner solar system, how their plasma tails develop as they approach the Sun, and how planetary atmospheres respond, or don't respond, to the passage of objects from beyond our cosmic neighbourhood. Venus before November 3rd was well characterised. Scientists had baseline measurements. They knew what normal looked like, and that's crucial for detecting anomalies, because you can't identify something unusual unless you know what usual looks like in the first place. The planet's thick atmosphere also meant that any effects from the comet encounter would need to be significant to penetrate to measurable levels. Small perturbations would be swallowed by the massive atmospheric system. Only substantial interactions would create signals strong enough to distinguish from Venus's natural variability. That set a threshold, a minimum level of interaction required to produce detectable evidence. Some researchers wondered if Venus's atmospheric density might actually help preserve evidence of interaction. Unlike Earth, where atmospheric effects can dissipate quickly, Venus's thick envelope might retain signatures of external influence for longer periods. Temperature changes might persist. Compositional variations might remain detectable for days after the initial interaction. If something happened, the evidence might linger, and that's the context scientists carried into the encounter window. They had a baseline understanding of Venus's normal behaviour. They had instruments capable of detecting various types of atmospheric and plasma interactions. They had predictions about what might happen based on models of comet-planet encounters, and they had the awareness that this was a unique opportunity, an interstellar visitor passing close to a major planet while we had the technology and positioning to observe the event. What they didn't fully anticipate was how complicated the interpretation of observations would become. Because science isn't just about collecting data, it's about interpreting that data correctly. And when you're dealing with phenomena you've never directly observed before, an interstellar comet encountering Venus, the interpretation becomes challenging. November 3rd arrived with all the instruments ready, all the observation plans in place, all the predictions made, and then reality provided the data. What that data showed, and more importantly what it meant, has been the subject of intense discussion ever since. Because some observations matched expectations perfectly, others raised questions that don't have simple answers, and a few pieces of evidence have sparked genuine scientific controversy about what 3I Atlas really is and what it might have done during those crucial hours near Venus. November 3rd, 2025 wasn't just another date on the astronomical calendar. It was the convergence point where an object from another star system would make its closest approach to Venus, while humanity watched with more capable instruments than we've ever had for such an event. The observation window was narrow, the opportunity was irreplaceable, and scientists around the world knew that whatever data they captured during those hours might be the only information we ever get about how an interstellar visitor interacts with a planet in our solar system. The geometry of the encounter was specific. 3I Atlas would pass Venus at a distance that placed the comet relatively close in astronomical terms, close enough that any extended structures from the comet might potentially reach the planet's atmospheric envelope. Not a collision, not even particularly close by everyday standards, but in the context of planetary encounters with cometary objects, close enough to matter. Multiple spacecraft had viewing opportunities, each positioned to observe different aspects of the encounter from different angles and with different instruments. Europa Clipper, making its way toward Jupiter for its mission to study the icy moon's subsurface ocean, happened to be travelling through the inner solar system during the encounter window. Its trajectory would potentially take it through the extended ion tail region if 3I Atlas was producing the kind of plasma tail astronomers expected as the comet approached the Sun. Think about what that means. Europa Clipper isn't designed to study comets, it's an ice moon mission. But the spacecraft carries instruments sensitive to charged particles and plasma environments because that's exactly what it needs to measure at Jupiter's radiation-intense system. Those same instruments could potentially detect if the spacecraft passed through cometary plasma, a bonus science opportunity that mission planners hadn't anticipated when designing the Jupiter journey years earlier. Here a spacecraft, fresh from its asteroid mission studying the aftermath of NASA's DART impact, also had viewing opportunities. Again, not designed for comet observation, but positioned where it could contribute data if mission controllers chose to point its instruments toward the encounter. Every available asset was being considered, every possible observation angle evaluated for what unique information it might provide. Then you had the dedicated solar observatories. SOHO has been watching the Sun continuously for decades, and its position gives it unique views of the inner solar system that can capture comets as they pass near our star. Parker Solar Probe, designed to fly closer to the Sun than any previous spacecraft, had angles that could track 3I Atlas as the comet approached perihelion. Solar Orbiter, the European NASA collaboration studying the Sun from multiple perspectives, added another viewpoint to the observation campaign. And Hubble, the venerable space telescope that has revolutionized our understanding of the cosmos, was scheduled to turn its ultraviolet spectroscopy capabilities toward 3I Atlas. Ultraviolet observations reveal what gases are sublimating from a comet's surface as solar heat turns ancient ice into vapor. Those spectral signatures tell scientists what elements and compounds exist in the comet's composition, providing a chemical fingerprint of material formed in another stellar system. The coordination required to make all of this happen is staggering. Each spacecraft has its own mission priorities, its own operational constraints, its own communication windows with Earth. Pointing a spacecraft in a different direction means not pointing it at something else. Activating instruments uses power and resources. Collecting data fills storage buffers and requires transmission time to send information back to Earth. Every observation represents choices, trade-offs, and scientific judgment about what's worth the investment of limited resources. But the scientific community decided 3I Atlas was worth it. The observation plans were approved, the spacecraft received their instructions. And as November 3rd approached, instruments were prepared to capture whatever the encounter would reveal. What were scientists hoping to see? The expectation list was comprehensive. If 3I Atlas was behaving like a typical comet, or at least like what scientists expected an interstellar comet to behave like, then several observable phenomena should occur. Gas emissions from sublimating ice would create a visible coma around the nucleus. Solar radiation pressure would push that gas and dust away from the Sun, creating the classic comet tail structure. Ionization of gases would create a separate plasma tail, glowing in ultraviolet light as charged particles interacted with the solar wind. If any of those structures extended far enough and the geometry was favourable, Venus might pass through them. Europa Clipper might transit through tail regions. Spectroscopic observations might detect compositional changes in Venus's upper atmosphere, indicating contamination from cometary material. Temperature sensors might pick up thermal signatures of atmospheric interaction. Even negative results would be valuable. If no interaction occurred despite favourable geometry, that would tell scientists something about how extended comet tails need to be to affect planetary atmospheres. If plasma instruments on spacecraft didn't detect tail material when they should have based on models, that would inform better predictions for future encounters. Science isn't always about discovering something unexpected. Sometimes it's about confirming predictions, validating models, and improving our understanding through observations that match expectations. The Venus encounter would be scientifically valuable, regardless of whether dramatic interactions occurred. But here's what makes science exciting. Sometimes observations don't match expectations. Sometimes the data contains surprises that force scientists to reconsider their models. Sometimes what instruments detect raises more questions than it answers, and that's exactly what happened. The data started coming back in the days following the encounter. First came the immediate observations, spacecraft telemetry, telescope images, spectroscopic measurements. Scientists began analysing what the instruments had captured, comparing observations against predictions, looking for signals of interaction or confirmation of expected behaviour. What they found was complicated. Some observations matched predictions beautifully. 3I Atlas was producing gas emissions consistent with cometary activity as solar heating increased approaching perihelion. Spectroscopic measurements detected expected volatile compounds. The basic physics of a comet responding to solar radiation appeared to be occurring as models suggested. But then came the observations that didn't fit as neatly into the expected framework. And that's where our story takes a turn from straightforward astronomy into genuine scientific mystery. Because in the weeks following the Venus flyby, images captured of 3I Atlas revealed features that have divided the astronomical community. Features that some scientists can explain with known comet physics, but that others find deeply puzzling. Features that have reignited debates about how we interpret observations of interstellar visitors and whether our assumptions about these objects might need fundamental revision. What were those features? What did astronomers see that sparked such controversy? And more importantly for our investigation, could any of what happened around 3I Atlas be connected to its encounter with Venus? Those questions bring us to the most fascinating and contentious part of this entire story, the anomalies that emerged in images captured in late November, and what they might reveal about the true nature of our mysterious interstellar visitor. Around November 20th, 2025, roughly 2.5 weeks after the Venus flyby, images of 3I Atlas started showing something that shouldn't exist according to conventional understanding of how comets behave. Astronomers had stacked multiple exposures to enhance faint details, a standard technique for teasing out subtle structures in astronomical objects. What appeared in those processed images sparked immediate debate. Extending from 3I Atlas were linear features projecting sideways relative to the expected tail orientation, not the classic tail streaming away from the sun. Not the dust and gas plumes that comets normally produce in all directions as their surfaces heat unevenly. These were straight lines extending perpendicular to where the main comet tail should be, reaching across vast distances of space with a geometry that struck multiple observers as unusual. Now, let's be clear about something important. Comets can produce complex structures. Fragmentation events create separate pieces that drift apart. Rotational effects can create curved features as spinning jets deposit material in spiraling patterns. Solar radiation pressure can push lightweight particles into trajectories that appear to branch away from the main tail. Experienced comet observers have seen plenty of unusual features over the decades, and most have straightforward explanations rooted in well-understood physics. But these features were different enough that they caught the attention of Harvard astronomer Avi Loeb, among others. Loeb, who has become a controversial figure in astronomy for his willingness to consider unconventional explanations for anomalous observations, published his analysis of the images. His observations focused on specific characteristics that he found difficult to reconcile with typical cometary behaviour. First was the orientation. The linear features extended sideways, perpendicular to the radial direction from the sun. Comet tails are fundamentally driven by solar radiation pressure and the solar wind, which push material radially outward from the sun. Dust particles, gas molecules and ionized plasma all get pushed in that same basic direction. creating the iconic tail that always points away from the sun regardless of which direction the comet is moving. Yet here were structures extending perpendicular to that expected orientation. Second was the straightness. When comets fragment or eject material, the resulting debris typically follows curved paths as gravity and radiation pressure combine to alter trajectories over time. A comet nucleus that's rotating will produce jets that sweep out curved patterns as the spinning surface changes which direction the jet points. These are well-documented phenomena. But the features in the 3i Atlas images maintained remarkable straightness over their entire visible length. Third was the speed implication. If these linear features were separate objects moving away from the main nucleus, calculating their apparent motion speed yielded numbers that Loeb and some other analysts found noteworthy. The features appeared to be moving at velocities higher than what you'd expect from typical cometary outgassing or fragmentation. Not impossibly fast, nothing violating physics, but fast enough to warrant notice and question where the energy for such velocities would come from. And fourth, perhaps most unusually, there were temperature anomalies reported in some observations of 3i Atlas as it approached the Sun. Instead of showing the expected temperature increases as solar radiation intensified, some measurements suggested temperatures near absolute zero even when the comet should have been experiencing significant solar heating. If accurate, those measurements don't align with how ice and rock respond to the Sun's energy. Let me emphasize something crucial here. These observations are from legitimate astronomical sources. The images are real, the measurements are genuine. What's in dispute isn't the data itself, it's the interpretation of what that data means. Most mainstream astronomers who have examined the same evidence offer conventional explanations. The linear features could be fragments from a fragmentation event that happened to orient in that configuration by chance. The straightness might be an illusion created by our viewing angle, where curved features appear straight when seen edge-on. The velocity calculations could be affected by measurement uncertainties or assumptions about the feature's actual distances from the main nucleus. The temperature readings might be instrumental artifacts or might reflect selective observation of particularly cold material within the cometary structure. These aren't dismissive explanations. They're scientifically legitimate interpretations based on known physics and documented comet behavior. Scientists who favor these conventional explanations aren't being close-minded. They're applying the principle that extraordinary claims require extraordinary evidence and that familiar explanations should be thoroughly exhausted before entertaining exotic alternatives. But Loeb and a minority of other scientists argue that while conventional explanations are possible, they require a combination of coincidences and special circumstances that collectively strain credibility. Yes, each individual anomaly might have a standard explanation. But when you encounter multiple unusual features simultaneously, odd orientation, unusual straightness, peculiar velocities, strange temperature readings, at some point you need to ask whether the conventional framework is being stretched beyond its reasonable limits. This is where scientific debate becomes fascinating. Both sides are looking at the same evidence, both are applying rigorous analysis, both are using the scientific method. Yet they're reaching different conclusions about what the observations mean. That's not a failure of science. That's science working exactly as it should when confronted with ambiguous data. Loeb's analysis goes further. He calculated that if the linear features were separate objects released from the main nucleus, their trajectories and speeds would be consistent with objects possessing some form of controlled motion rather than purely ballistic trajectories. He emphasized, and this is important, that he's not claiming 3i Atlas is artificial. He's asking whether the observations allow us to definitively rule out that possibility, and arguing that the answer is no. That distinction matters. Saying, this is definitely alien technology, is a positive claim requiring overwhelming evidence. Saying, we cannot definitively rule out artificial origin based on current observations, is a much weaker claim, a statement about the limits of our knowledge rather than an assertion of exotic reality. Loeb positions himself in the latter camp, arguing that scientific integrity demands we acknowledge when observations remain genuinely ambiguous. His critics counter that this approach amounts to what they call clickbait astronomy, generating public attention and media coverage by emphasizing exotic possibilities without sufficient evidence to justify such speculation. They argue that Loeb's pattern with Oumuamua, and now with 3i Atlas, represents a departure from responsible scientific communication that favors sensational interpretations over prosaic, but more likely explanations. The debate has become personal at times, with scientists on both sides questioning each other's motivations and methods. That's unfortunate because it obscures the legitimate scientific questions at the heart of the controversy. Whether or not you find Loeb's interpretations persuasive, the observations he's highlighting are real and do warrant scientific explanation. So, what about Venus? Could any of these anomalous features be related to the planetary encounter that occurred weeks earlier? Here's where speculation becomes almost unavoidable, because the connection, if any exists, isn't obvious from the available data. One hypothesis some have floated is that the Venus close approach might have triggered fragmentation through tidal forces or atmospheric interaction, and that the linear features represent fragments created during that encounter. This would be testable by analysing whether the fragments' trajectories trace back to the Venus vicinity, but such analysis requires precise trajectory data that may not be available yet. Another idea, far more speculative, is that if 3i Atlas possessed any kind of internal structure or mechanisms which remains entirely unproven, the gravitational interaction with Venus might have activated some kind of response. This ventures into pure speculation territory, but it's the kind of question that arises when observations don't fit neatly into conventional boxes. The more conservative perspective is that whatever we're seeing with 3i Atlas's unusual features has nothing to do with Venus at all. The timing might be coincidental, with the linear structures developing as the comet approached perihelion, and solar heating intensified, triggering outbursts or fragmentation that would have happened regardless of any planetary encounter. What we need to be honest about is this: the observations remain ambiguous. Multiple interpretations are possible. The evidence doesn't yet definitively favour any single explanation to the exclusion of others, and that ambiguity is precisely what makes this situation scientifically interesting and frustratingly unsettled. Additional observations might resolve the uncertainty. If the linear features persist and continue behaving in ways incompatible with known physics, that would strengthen the case for exotic explanations. If they dissipate or evolve in ways consistent with fragmentation debris, that would support conventional interpretations. If future analysis of the Venus encounter reveals clear evidence of atmospheric interaction or lack thereof, that might inform whether the encounter played any role in subsequent observations. But right now, in the immediate aftermath of this extraordinary flyby, we're in that uncertain space where honest scientists can look at the same data and reach different conclusions, where the gap between what we observe and what we can definitively explain creates room for both conventional and unconventional hypotheses to coexist without either being proven beyond doubt. And that brings us to perhaps the most important question of all: what happens next? Because 3i Atlas isn't finished with its journey through our solar system. More observations are coming, better data is being collected, and the scientific investigation into what this interstellar visitor truly is and what it did near Venus is far from over. Now let's address the question that should be nagging at you by now. Did 3i Atlas actually do anything to Venus? Or was the encounter essentially a cosmic near-miss with no meaningful interaction? The answer depends on what kind of interaction we're talking about, and what threshold of evidence we require to conclude something happened. Start with the most straightforward possibility: plasma interaction between the comet's ion tail and Venus's upper atmosphere. This is basic plasma physics. When a comet approaches the Sun, solar ultraviolet radiation ionizes some of the gas sublimating from the comet's surface. That ionized gas, plasma, gets caught up by the solar wind and pushed away from the Sun, creating the glowing ion tail visible in many comet photographs. That tail can extend for enormous distances, potentially spanning millions of kilometers behind the comet nucleus. If Venus passed through that ion tail region, or if the tail's geometry brought ionized material into contact with Venus's atmospheric envelope, then charged particles from interstellar space would interact with molecules from Venus's atmosphere. The interaction would create a region of mixed plasma, potentially generating local magnetic field perturbations, temperature variations, and compositional changes detectable by the right instruments. This kind of interaction isn't hypothetical. Earth has passed through cometary debris streams multiple times in recorded history. Those encounters produce meteor showers as small particles burn up in our atmosphere, and they create measurable effects in Earth's upper atmospheric chemistry that scientists can detect with specialized instruments. Venus, lacking Earth's strong magnetic field that normally deflects much solar wind and charged particle radiation, would arguably be more susceptible to direct plasma interaction if it occurred. The question is whether the geometry and distances involved in the November 3rd encounter would bring 3I Atlas's ion tail close enough to Venus to create detectable effects. Pre-flyby models made predictions based on estimated comet outgassing rates, solar wind speeds, and the magnetic structures that form around comets as they interact with the Sun's plasma environment. Some models suggested possible interaction. Others calculated that distances were too great for significant effects. Europa Clipper's trajectory offered a potential way to test these predictions. If the spacecraft passed through ion tail plasma, its instruments would detect the charged particle environment directly. The data from Europa Clipper during the encounter window could tell scientists whether the comet's plasma structures extended far enough to reach the Venus vicinity, or whether the tail was more limited than some predictions suggested. As of the information available, NASA hasn't released dramatic announcements about Europa Clipper detecting clear evidence of comet tail plasma interaction. That could mean several things. Maybe the spacecraft didn't pass through tail regions after all. Maybe it did, but the instruments weren't configured to capture that specific data optimally. Maybe the interaction occurred but was subtle enough that analysis is still ongoing. Or maybe the tail structures simply didn't extend as far as the more optimistic models predicted. The absence of immediate dramatic announcements doesn't mean nothing happened. Space science moves slowly, data analysis takes time, peer review demands thorough examination before conclusions are published. Some of the most important discoveries in astronomy were initially ambiguous observations that required months or years of careful analysis to understand properly. So what might Venus have experienced if plasma interaction occurred? The effects would likely be subtle and transient. Venus's massive atmosphere wouldn't be fundamentally altered by a brief encounter with cometary plasma. We're not talking about dramatic visible changes or persistent effects that would transform the planet. Instead, think of it as a temporary perturbation, a ripple in the atmospheric system that would create measurable signals for instruments watching at the right time with the right sensitivity. Temperature variations might appear in the upper atmospheric layers where plasma interaction would occur. Compositional measurements might detect small amounts of elements or compounds characteristic of cometary material, carbon, nitrogen, sulfur compounds, appearing at altitudes where they're not normally present. Atmospheric circulation patterns might show brief disruptions, as local heating or charged particle impacts created temporary pressure variations. All of these effects would be challenging to detect and even more challenging to definitively attribute to the comet encounter rather than Venus's natural atmospheric variability. Venus's atmosphere is turbulent and complex. Temperature fluctuations happen naturally. Compositional variations occur as different atmospheric layers mix. Isolating a specific signal caused by external influence requires extremely careful analysis and comparison with baseline observations from periods when no encounter occurred. Here's where the scientific challenge becomes apparent. Even if instruments detected atmospheric changes during the encounter window, proving causation, proving those changes were definitely caused by 3I Atlas rather than coincidental natural variability, requires meeting high standards of evidence. You'd need to show that the observed changes were statistically significant beyond normal variation, that they occurred specifically during the encounter window rather than randomly before or after, and that they matched the expected signature of comet-atmosphere interaction rather than some other process. Meeting those standards with the observations available is difficult, and that difficulty is reflected in the scientific literature and announcements about the encounter. We haven't seen papers definitively declaring 3I Atlas demonstrably affected Venus's atmosphere, nor have we seen definitive declarations that no interaction occurred. Instead, we're in the realm of ongoing analysis where scientists are still working through the data, comparing models with observations, and attempting to extract clear signals from noisy measurements. But there's another layer to this question that ventures into more speculative territory. What if the interaction between 3I Atlas and Venus involved mechanisms beyond standard plasma physics? What if, and this is where conventional scientists would urge extreme caution, the interstellar visitor possessed properties or capabilities that our current models don't account for? This is where Loeb's observations about the linear features potentially being related to the Venus encounter gain their most speculative interpretation. If, and this is a very large if, Those features represented some kind of response or reaction to the planetary encounter. What would that imply? It would suggest internal processes within 3I Atlas, beyond passive ice sublimation and fragmentation. It would hint at mechanisms we don't currently understand operating within or on the object. Most scientists would rightfully demand extraordinary evidence before entertaining such exotic hypotheses. The burden of proof falls on those suggesting unusual mechanisms to demonstrate that conventional explanations are genuinely inadequate, and that demonstration hasn't been made to the satisfaction of the broader scientific community. Yet here's what's undeniable. Something unusual appeared in observations of 3I Atlas in the weeks following the Venus flyby. Whether those features have anything to do with Venus, or whether they're entirely unrelated developments that happened to occur after the encounter by coincidence, remains unresolved. The correlation in timing doesn't prove causation, but it does raise a question that deserves investigation. What would convince scientists that a genuine Venus-related effect occurred? Strong evidence would include clear measurements from multiple independent instruments showing atmospheric or compositional changes at Venus during the encounter that matched predicted signatures of comet interaction. It would include trajectory analysis of any fragments or features showing they originated from the Venus vicinity at the encounter time. It would include theoretical modelling demonstrating how the observed effects could be produced through known physics operating under the encounter conditions. Weaker evidence, what we currently have, includes interesting observations whose interpretation remains ambiguous, timing correlations that might be coincidental, and features that could have multiple explanations. That doesn't mean the observations are unimportant. It means they're not yet conclusive. And that's an honest assessment of where we stand. The Venus encounter happened. It was observed by multiple instruments from multiple vantages. Data was collected. Subsequent observations of 3I Atlas revealed unusual features. Whether those pieces connect in a meaningful cause and effect relationship, or whether they're separate phenomena that happen to occur in sequence, remains an open question. Science often operates in this space of uncertainty longer than the public realizes. The textbook version of scientific discovery makes it seem like observations lead directly to clear conclusions. The reality is messier. Observations lead to multiple competing interpretations. Evidence accumulates gradually. Debates continue as scientists with different perspectives analyze data through different lenses. Eventually, sometimes quickly, sometimes over years, consensus emerges as evidence favours certain interpretations over others. We're still in the early phase of that process with 3I Atlas. The Venus encounter was just weeks ago. The unusual features appeared recently. Scientists are still analysing, still modelling, still debating what the observations mean. Definitive conclusions may take months or years to crystallise as more data becomes available and as analysis techniques improve. What's certain is that the encounter provided a unique opportunity to study an interstellar object under unusual circumstances. Whether that opportunity revealed anything truly anomalous, or whether it simply added more data points to our understanding of how comets behave, is the central question driving current research. And the answer to that question will inform how we approach future interstellar visitors, what observations we prioritise, and whether our current theoretical framework for understanding these objects is adequate or needs expansion. The Venus connection may prove to be the key that unlocks understanding of 3I Atlas's true nature, or it may prove to be a fascinating but ultimately coincidental timing of separate events. Either way, the scientific investigation continues, and the questions raised by this encounter will shape how we study the next interstellar visitor whenever it arrives. No discussion of 3I Atlas would be complete without directly addressing the elephant in the astronomical room, the possibility that this interstellar visitor might be something other than a natural object. And that brings us to Avi Loeb, Harvard's iconoclastic astrophysicist who has become simultaneously one of the most prominent and most controversial voices in the discussion about interstellar objects. Loeb's involvement in this debate didn't start with 3I Atlas. It began with Oumuamua, the first confirmed interstellar visitor, back in 2017. Oumuamua exhibited strange acceleration as it left the solar system, a small but measurable deviation from the trajectory that gravity alone would produce. Most astronomers attributed this to outgassing, the same rocket-like effect that propels conventional comets when ice sublimates asymmetrically. Loeb noticed that Oumuamua showed no visible coma or tail, no clear evidence of the outgassing that supposedly explained its acceleration. He proposed an alternative. What if Oumuamua was being pushed by solar radiation pressure? And what if it had an unusually large surface area relative to its mass, like a thin sail? That would explain the acceleration without requiring invisible outgassing. And if you're going to propose a sail-like geometry, well, what naturally occurring object has that shape? Loeb didn't definitively claim Oumuamua was artificial, but he argued the possibility couldn't be ruled out and deserved serious scientific consideration. The astronomical community's reaction was swift and largely critical. Most scientists felt Loeb was jumping to exotic explanations without exhausting conventional possibilities. They pointed out that outgassing from specific volatile ices could explain Oumuamua's behavior without requiring artificial origins. They argued that entertaining alien technology explanations without compelling evidence crossed the line from reasonable speculation into attention-seeking sensationalism. Loeb countered that science requires following evidence wherever it leads, even when that direction makes people uncomfortable. He argued that dismissing possibilities without thorough investigation is just as unscientific as accepting them without evidence. And he pointed out that the history of astronomy is filled with examples where the conservative scientific consensus was eventually overturned by observations that initially seemed impossible. Now, years later, the same dynamic is playing out with 3I Atlas. Loeb has examined the observations, the linear features, the unusual orientations, the temperature anomalies, the trajectory characteristics, and he's asking the same uncomfortable question. Can we definitively rule out artificial origin based on what we're seeing? His argument isn't that 3I Atlas is definitely artificial, it's that the observations contain elements that don't fit comfortably within conventional comet physics, and that scientific integrity demands we acknowledge the limits of our certainty. He emphasizes that he's not claiming aliens are visiting us. He's claiming that our data doesn't yet allow us to definitively exclude that possibility, and that excluding it prematurely would be bad science. What specific features does Loeb point to? Start with those linear structures extending sideways from the main nucleus. If these are separate objects that were released from 3I Atlas, their straight-line trajectories and apparent velocities suggest something beyond typical fragmentation physics. Loeb has calculated the energies required to accelerate objects to the observed speeds and notes that exceed what normal cometary outgassing typically produces. Then there's the trajectory alignment with our solar system's planetary plane. Yes, this could be coincidental. Eventually some interstellar object will randomly happen to enter aligned with our planetary system. But Loeb notes that the probability isn't overwhelmingly high for any random visitor, and that alignment becomes more interesting when combined with other unusual observations. The temperature anomalies constitute another piece of his argument. If 3I Atlas is showing temperatures near absolute zero despite approaching the Sun, that suggests some mechanism is preventing solar heating from affecting the object normally. What mechanism? Conventional explanations might involve highly reflective surfaces or specific material compositions that don't absorb solar radiation efficiently. Loeb suggests we should also consider whether artificial materials might produce such observations. And there's the broader statistical argument Loeb makes. He points out that in a galaxy containing hundreds of billions of stars, many of which likely host planetary systems, the existence of technological civilizations becomes a question of probability. If even a small fraction of stellar systems develop technology, and if a small fraction of those civilizations build probes or instruments to explore beyond their home systems, then the galaxy should contain a substantial number of artificial objects drifting through interstellar space. If such objects exist in any significant numbers, Loeb argues, then our solar system will occasionally be visited by them, just as we're occasionally visited by natural interstellar objects like asteroids and comets. When we detect an interstellar visitor behaving unusually, shouldn't we at least investigate the possibility that we've encountered one of those artificial travelers rather than immediately assuming it must be natural? His critics respond on multiple fronts. First, they argue that invoking artificial origins without compelling evidence violates the principle of Occam's razor, the idea that simpler explanations should be preferred over more complex ones when both fit the observations. A natural comet behaving in unusual but ultimately explainable ways is simpler than an alien probe, so that's what we should default to unless forced otherwise by evidence. Second, they point out that our understanding of comet physics is still developing, especially for interstellar comets, which we've only observed a handful of times. What appears anomalous now might simply reflect our limited experience with these objects. As we observe more interstellar visitors, we'll develop better models that may naturally explain the features that currently seem strange. Third, and perhaps most pointedly, critics accuse Loeb of using sensational possibilities to generate media attention and public interest without the scientific rigour that should accompany such extraordinary claims. They suggest his approach has more to do with publicity than legitimate scientific inquiry, and that it damages the credibility of astronomy by associating the field with speculative claims about aliens. Some of the criticism has become quite personal. Scientists have publicly called Loeb's work on interstellar objects clickbait, and accused him of betraying scientific standards for fame and book deals. Loeb has responded that his critics are close-minded and unwilling to consider evidence that challenges their comfortable assumptions. This is unfortunate, because the personal animosity obscures what should be a productive scientific debate. Set aside the personalities and egos for a moment. The fundamental question is entirely legitimate. When we observe interstellar objects behaving in ways we don't fully understand, what's the appropriate scientific response? Conservative scientists argue that we should exhaust natural explanations before entertaining artificial ones, and that the bar for considering artificial explanations should be extremely high. They're right that scientific caution is important, and that accepting extraordinary claims without extraordinary evidence would be poor practice. But Loeb makes a valid point that outright dismissing possibilities without investigation is equally unscientific. If we reflexively assume every anomalous observation must have a conventional explanation, and never seriously investigate alternative hypotheses, we might miss genuinely revolutionary discoveries. The productive middle ground is this: treat artificial origin as a hypothesis to be tested rather than either accepted or dismissed a priori. What observations would definitively indicate artificial rather than natural origin? Design instruments and observation campaigns that could detect those signatures. Apply the same rigorous analysis to both conventional and unconventional hypotheses, and let the data determine which explanations survive scrutiny. That's not what's happening in the 3i Atlas debate, unfortunately. Instead, we have camps talking past each other, with Loeb highlighting anomalies and his critics explaining them away with conventional physics, and neither side acknowledging the legitimate uncertainties that exist in our current understanding. What would actually settle the debate? Clear evidence is what science demands. If 3i Atlas exhibited behaviour that definitively violated known physics, if it performed manoeuvres requiring propulsion, if it emitted signals, if it demonstrated capabilities that no natural process could produce, then the artificial hypothesis would gain overwhelming support regardless of scientists' initial skepticism. Conversely, if continued observation shows the unusual features evolving in ways fully consistent with complex but natural cometary processes, if the anomalies disappear or resolve into well-understood phenomena, then the conventional interpretation would be vindicated and the artificial speculation would fade. Right now we're in the uncomfortable middle zone where observations are ambiguous enough that both interpretations remain marginally plausible. That ambiguity won't last forever. More data is coming, better analysis will emerge, and within months or years, scientific consensus will likely form around an interpretation that commands broad acceptance. Whether that consensus validates Loeb's willingness to consider unconventional possibilities or vindicates his critics' insistence on conventional explanations remains to be seen. But the debate itself illustrates an important truth about science. It's not a set of established facts. It's a process of investigation that sometimes requires entertaining uncomfortable ideas to ensure we're not prematurely closing doors that should remain open. The Venus encounter adds another dimension to this debate. If investigation eventually reveals that something genuinely unusual occurred during that flyby, something that can't be explained with standard planetary-comet interaction physics, then the case for 3i Atlas being more than a typical comet becomes stronger. If Venus emerges as simply a coincidental timing with no meaningful connection to the object's unusual features, then conventional explanations gain support. Either way, the scientific story continues to unfold, and the questions raised by this interstellar visitor ensure that astronomers will be watching closely as 3i Atlas continues its journey through our solar system and eventually back into the interstellar void from which it came. The story of 3i Atlas and its Venus encounter isn't over, not by a long shot. Right now, at this moment, telescopes are tracking this interstellar visitor as it continues its journey through our solar system. Spacecraft are collecting data, scientists are analysing observations, and more opportunities to study this mysterious object are coming in the weeks and months ahead. December 2025 brings one of the most anticipated observations yet. The James Webb Space Telescope is scheduled to turn its unprecedented infrared capabilities toward 3i Atlas. JWST represents the most powerful infrared observatory humanity has ever built, capable of detecting thermal emissions and analysing compositions with sensitivity that ground-based telescopes simply cannot match. What JWST observes could potentially resolve some of the current ambiguities. Infrared observations reveal temperature distributions across an object's surface. They detect what compounds are sublimating based on their characteristic spectral signatures. They can identify complex organic molecules, water ice, carbon dioxide, methane, and dozens of other materials by their unique infrared fingerprints. If 3i Atlas is a conventional comet, JWST should see compositional signatures consistent with known solar system comets, or perhaps reveal exotic compounds characteristic of formation in a different stellar environment. If something stranger is occurring, JWST might detect thermal patterns that don't match expectations for solar heating of passive ice and rock. It might see compositional anomalies that challenge our understanding of what interstellar objects should be made of, or it might confirm conventional composition and thermal behaviour, strengthening the case that 3i Atlas is an unusual-looking but ultimately natural comet. Hubble continues its observation campaign as well. Ultraviolet spectroscopy tracks gas emissions as the comet's activity level changes with distance from the Sun. Every spectrum captured adds to the dataset scientists will use to model what's happening to this object. Over time, patterns emerge. Outgassing rates might show expected changes as solar heating varies, or they might show irregularities that demand explanation. Ground-based telescopes worldwide are contributing observations as 3i Atlas moves through the constellations of Virgo and Leo in the coming months. Professional observatories with large mirrors can capture detailed images showing how those controversial linear features evolve over time. Amateur astronomers with sophisticated equipment are also tracking the comet, creating a distributed observation network that ensures continuous monitoring even when professional facilities are scheduled for other projects. This kind of sustained observation campaign is relatively rare. Most comets don't warrant such intensive scrutiny. But 3i Atlas's interstellar origin and unusual features have elevated it to special status, where every available instrument that can contribute data is being utilized to maximum effect. The brightness predictions suggest 3i Atlas will remain observable for months as it recedes from the Sun, though it will gradually fade as solar heating decreases and the comet's activity level drops. The window for detailed observation is limited. Within several months, the object will become too faint for all but the largest telescopes to study effectively. That makes the current period crucial. This is our best chance to gather comprehensive data before 3i Atlas fades into obscurity. But there's another encounter coming that has scientists particularly interested. In March 2026, 3i Atlas will make its closest approach to Jupiter. Now, it won't be nearly as close to Jupiter as it passed Venus. The geometry is different, the distance is larger. But Jupiter's massive gravitational field and complex magnetosphere create an environment where even distant encounters can produce observable effects. Jupiter is surrounded by intense radiation belts, powerful magnetic field structures, and a system of moons that provide multiple vantage points for observation. The Juno spacecraft currently orbiting Jupiter might have opportunities to observe 3i Atlas from its unique position. Ground-based telescopes watching Jupiter could potentially detect any interactions between the comet and Jupiter's extended magnetosphere. What scientists will be looking for is consistency. Does 3i Atlas continue exhibiting the unusual features observed after the Venus encounter, or do those features dissipate and disappear? Does the object's trajectory remain perfectly consistent with gravitational dynamics, or do any additional non-gravitational accelerations appear? Does continued spectroscopic observation reveal anything unexpected about composition or outgassing patterns? These ongoing observations serve multiple purposes. They test competing hypotheses about what 3i Atlas is and how it's behaving. They provide data that will inform how we approach future interstellar visitors, and they contribute to the growing dataset of interstellar object observations that will eventually allow scientists to understand how typical or atypical each individual visitor turns out to be. One crucial aspect of modern astronomy is that observations aren't kept secret. Scientists publish their data, share their findings through papers and conferences, and make measurements available to the broader research community. That means independent teams can analyze the same observations, check each other's conclusions, and identify errors or alternative interpretations that a single research group might miss. This collaborative, transparent process is how scientific consensus eventually emerges. It's not about one charismatic scientist convincing everyone else to accept their interpretation. It's about multiple independent researchers examining evidence, testing hypotheses, and gradually converging on explanations that best fit the totality of available data. For 3i Atlas, that process is ongoing. Papers are being written analysing various aspects of the encounter and subsequent observations. Conferences will feature presentations debating interpretations. Peer reviewers will scrutinise claims for weaknesses or unwarranted assumptions. It's messy and slow, but it's how science separates reliable conclusions from preliminary speculation. What should you watch for in coming months as this story continues to develop? First, look for any announcements about JWST observations and what they reveal about composition and thermal behaviour. Those could be game changers for understanding what 3i Atlas actually is. Second, pay attention to whether the controversial linear features persist, evolve, or disappear. Their fate will inform whether they represent genuine anomalies requiring exotic explanation, or transient structures that ultimately fit within conventional comet physics. Third, watch for any evidence emerging about the Venus encounter itself. Did Europa Clipper or other spacecraft detect clear signals of atmospheric interaction? Have scientists analysing Venus observation data found any atmospheric changes corresponding to the flyby timing? Positive findings would elevate the encounter from interesting coincidence to meaningful event. And fourth, keep an eye on the ongoing Loeb controversy. Will additional observations vindicate his willingness to consider unconventional interpretations, or will they support his critics' insistence that conventional explanations suffice? Science has a way of resolving these debates eventually, even when the personalities involved make the process more dramatic than necessary. The ultimate fate of 3i Atlas is already determined by physics. After passing Jupiter in March, it will continue outward, eventually leaving our solar system entirely and returning to the interstellar medium from which it came. Within years, it will be too distant for even our best telescopes to detect. It will become once again just another unseen traveller in the vast galactic ecosystem of objects drifting between the stars. But the data we collect during its brief passage through our neighbourhood will remain. That data will be analysed and reanalysed for years, contributing to our understanding of what exists beyond our solar system and what we should expect from future interstellar visitors. Every measurement adds to our knowledge. Every observation informs our models. Every interstellar object we successfully study brings us incrementally closer to understanding the galaxy we inhabit. And that brings us to the final question. What does all of this mean? Why should you care about an icy rock from another star system that briefly passed our neighbouring planet? What significance does this encounter hold beyond the immediate scientific curiosity it generates? Step back for a moment from the details about trajectories and plasma interactions and scientific controversies. Look at the bigger picture of what's actually happening here. For the first time in human history, we're developing the capability to routinely detect, track, and study objects that originated in other stellar systems. Think about what that means. For all of human existence until just a few years ago, everything we studied in the sky either belonged to our solar system or was so distant that we could only observe it passively with light that travelled for years or millennia to reach us. Planets, moons, asteroids, comets, all members of our local cosmic family. Stars, galaxies, nebulae, beautiful but untouchably remote. Interstellar objects occupy a unique middle ground. They're not from here, yet they pass close enough that our instruments can analyse them in detail. They're travellers from distant places, carrying information about environments and processes occurring around other stars. They're like messages in bottles thrown into the galactic ocean, washing up on our shore for brief moments before drifting away again. Umama was the first confirmed bottle we found. Tui Borisov was the second. Now 3i Atlas is the third. Each one taught us something different. Each one revealed that interstellar visitors come in varieties we hadn't anticipated. Each one raised questions about how typical our solar system is compared to the wider galactic environment where these objects formed. And here's what's remarkable. We're detecting more of them because our technology is getting better, not because more are arriving. The galaxy has always been filled with these travellers. Countless objects drift through interstellar space, most following trajectories that never bring them near any star system, others occasionally passing through stellar neighbourhoods like ours. They've been there all along. We simply couldn't see them until we built automated sky surveys sensitive enough to spot their faint signatures against the background stars. That technological capability is accelerating. New surveys coming online in the next decade will detect interstellar visitors far more frequently. What once seemed like rare cosmic events will become routine observations. We'll build statistical samples large enough to understand how common different types of interstellar objects are. We'll learn whether our solar system's comets and asteroids are typical, or whether we're the weird ones in a galaxy full of different varieties. The Venus encounter adds scientific value beyond just the flyby itself. It's the first time we've observed an interstellar object having a close encounter with a major planet, while we had the instruments and positioning to potentially detect interactions. That's unprecedented. Even if the encounter produced no dramatic effects, the observations establish baselines for what doesn't happen when an interstellar comet passes a planet. If effects did occur, if Venus's atmosphere responded measurably to 3I Atlas's passage, then we've witnessed the first confirmed interaction between interstellar material and a solar system planet. That's fundamentally significant for understanding how material migrates between stellar systems, how planetary atmospheres respond to external influences, and what kinds of exchange processes might occur when interstellar visitors pass through inhabited systems. Think about the implications in the context of life and planetary habitability. Earth has certainly been visited by interstellar objects throughout its history, just as Venus was potentially visited by 3I Atlas. We weren't watching for most of that history, but the visits happened. Did any of those ancient encounters deliver materials to Earth's atmosphere? Could organic compounds from other stellar systems have contributed to the chemical inventory from which life emerged? These aren't wild speculations. Scientists seriously study panspermia hypotheses, the idea that life's building blocks or even simple organisms might be transported between stellar systems via interstellar objects. Most experts consider it unlikely that life itself travels this way, but the transport of complex organic molecules is entirely plausible. Comets contain rich organic chemistry. Interstellar comets carry organics formed under different stellar conditions. When they encounter planets, some material exchange could occur. Whether or not 3I Atlas contributed anything to Venus's atmospheric chemistry, the principle holds. Interstellar visitors have been mixing materials between stellar systems for billions of years. Our solar system's chemical inventory isn't purely local. It includes contributions from interstellar space, delivered by objects like 3I Atlas. Now address the artificial question one more time, because it matters to the bigger picture. If, and this remains highly speculative, if any interstellar visitors turn out to be artificial rather than natural, what would that mean? It would mean we're not alone in the galaxy. It would mean other technological civilizations exist and have developed the capability to send instruments or probes beyond their home systems. It would mean the galaxy contains not just natural processes, but also the products of intelligence and engineering. That would be the most profound discovery in human history. It would reframe our understanding of our place in the universe more dramatically than any previous scientific revolution. It would raise questions about why we're being visited, whether communication is possible, and how humanity should respond to the knowledge that we share the galaxy with others. But here's the crucial caveat. We don't have evidence that this is the case. Not yet. The ambiguous observations of 3I Atlas, like the earlier ambiguities of Oumuamua, don't constitute proof of artificial origin. They constitute interesting data that hasn't been definitively explained yet. There's a vast difference between not yet explained and artificial. Science requires we maintain that distinction rigorously. Being open to possibilities isn't the same as accepting them without sufficient evidence. And right now, the evidence doesn't support concluding that 3I Atlas is anything other than a natural object, even if it's a natural object exhibiting behaviors we don't fully understand yet. So whether 3I Atlas is natural or artificial, and the overwhelming probability favors natural, the encounter matters. It matters because it advances our observational capabilities and our understanding of what travels through the galaxy. It matters because it demonstrates that we can mobilize coordinated observation campaigns when rare opportunities arise. It matters because the scientific debates it's generating will refine our methods for interpreting ambiguous observations. And it matters because it reminds us that we live in a dynamic galaxy where our solar system isn't isolated. We're part of a vast ecosystem where materials and objects move between stellar systems, where encounters like the Venus flyby happen regularly on cosmic timescales, and where our increasing technological sophistication allows us to observe and study processes that our ancestors could never have imagined. Every interstellar visitor we detect expands our cosmic perspective. We're no longer limited to studying just our own solar system's inventory. We're beginning to sample what exists beyond, to compare different stellar environments, to understand how the galaxy's chemical and physical evolution creates the diversity of objects we're discovering. 3i Atlas won't be the last mysterious visitor. It won't be the last object that generates scientific debate and ambiguous observations. As detection capabilities improve, we'll encounter interstellar travelers regularly, some clearly conventional, some puzzlingly unusual, and perhaps eventually one that provides definitive evidence of something extraordinary. But regardless of whether extraordinary discoveries lie ahead, the ordinary discoveries are valuable too. Every confirmed interstellar object adds to our understanding. Every successful observation campaign demonstrates our growing capability to study these cosmic travelers. Every scientific debate about interpretation refines our methods and reminds us that the universe still holds mysteries we're working to comprehend. Venus has been visited before by spacecraft we built and sent to explore our neighbouring planet. But it had never, at least not in the brief period we've been watching, been visited by something from another star. What that visit revealed, or didn't reveal, will be debated for years. The data will be analysed and reanalysed. Competing interpretations will be tested against continued observations, and eventually scientific consensus will emerge about what 3i Atlas truly was and what its encounter with Venus actually meant. Until then, we have the privilege of witnessing science in action. We see the messy process of investigation, the uncertainty that precedes clarity, the debates that eventually resolve into understanding. We're living through a moment when humanity's cosmic awareness is expanding, when we're transitioning from observers of our local neighbourhood to students of the broader galaxy. And that's why this story matters. Not because one specific comet passed one specific planet, but because that event represents humanity, reaching a new threshold of capability and awareness. We're no longer confined to wondering what might exist beyond our solar system. We're beginning to observe it directly, to study it rigorously, and to understand our place within the vast galactic community of matter and motion. The encounter between 3i Atlas and Venus is just one chapter in that larger story. But it's a chapter worth paying attention to, because it's a glimpse of the discoveries and questions that await as we continue learning to recognize and understand the travelers from beyond who pass through our cosmic neighborhood. Some will be mundane, some will be fascinating, and perhaps someday one will be extraordinary. Until then, we watch, we measure, we debate, and we learn. That's how science advances. That's how humanity expands its understanding. And that's why what happened at Venus on November 3rd, 2025, deserves your attention and your curiosity.